Out there, in the vast darkness of space, lies one of the universe's most bewildering puzzles. A cosmic dance so rare, so strange, that until recently, scientists weren't even sure it could exist. Picture not one, not two, but 7 stars locked in an intricate gravitational embrace, swirling around one another in a celestial ballet that defies everything we thought we knew about star systems. These are septuple star systems, astronomical anomalies so unusual that discovering one feels like stumbling upon a hidden chapter in the universe's grand storybook. And yet, the deeper we look, the more mysteries they unravel. What could possibly keep 7 massive stars from tearing each other apart? How do they maintain their delicate balance across billions of years? The answers are as mind-bending as the systems themselves. Some of these stellar families host stars that eclipse one another in perfect rhythms, casting shadows across the cosmos. Others fling rogue members into the void, creating unpredictable orbits that challenge our understanding of gravity. And then there are the ones hiding secrets we've only begun to decipher: strange magnetic fields, unexplained energy bursts, even hints of planets caught in the chaos, clinging to survival in a sky filled with multiple suns. This is the frontier of cosmic discovery, where every new observation rewrites the rules. Over the next few minutes, we're diving into 30 of the most astonishing revelations about these stellar enigmas, from the way they form against all odds, to the eerie signals they emit, to the lingering questions that keep astronomers awake at night. Whether you're a space enthusiast or just someone who loves a good mystery, buckle up. The universe is about to show you one of its most spectacular, head-scratching performances. And trust me, by the end, you'll never look at the night sky the same way again. The first time astronomers caught definitive proof of a 7-star system, it sent shockwaves through the scientific community. Nestled within the constellation Orion, over 450 light-years from Earth, the system known as New Scorpii shattered expectations. For decades, telescopes had spotted hints of multiple stars orbiting one another in this region, but piecing together their exact configuration was like untangling a cosmic spiderweb. Researchers relied on a combination of high-resolution spectroscopy and interferometry, tools so precise they can detect the subtle wobbles and shifts in starlight caused by gravitational tugs between stars. Even then, confirming 7 distinct members required years of patient observation, as each new layer of the system revealed itself like a Russian nesting doll of stellar bodies. What made this discovery so groundbreaking wasn't just the number of stars, it was the sheer improbability of their stability. Most multi-star systems cap out at 3 or 4 members. Beyond that, gravitational chaos typically tears them apart. Yet here was New Scorpii with 2 tightly paired binary stars orbiting a central triplet, all while another distant binary danced around the outskirts. The system's hierarchy resembled a meticulously choreographed routine, with each group maintaining its orbit without collapsing into mayhem. But the real challenge lay in distinguishing between true septuple systems and accidental alignments of unrelated stars. Early skeptics questioned whether some of New Scorpii's components might just be passing neighbors, not genuine gravitational partners. It took advanced computer simulations, tracking the star's motions over years, to prove these 7 were irrevocably bound. Even now, astronomers debate how such a fragile arrangement could survive the turbulent births of its stars, where violent gas clouds and competing gravitational pulls should have scattered them to the cosmic winds. The answer, it seems, lies in a delicate balance of mass and distance, a celestial tightrope act where one wrong move could spell disaster. New Scorpii's discovery didn't just add a new oddity to the astronomy books. It forced scientists to rethink the limits of stellar kinship, proving that the universe's creativity far outpaces our imagination. And if a system this complex could exist, hidden in plain sight for centuries, what other breathtaking configurations might be waiting to be found? Gravity in a septuple star system doesn't play by the rules we're used to. In most binaries or even triple systems, stars settle into predictable, almost clockwork orbits. But cram 7 massive bodies into a tight cosmic neighborhood, and the stability vanishes, replaced by a swirling maelstrom of gravitational turmoil. Some of these systems feature stars whipping around each other at distances closer than Mercury orbits our Sun, their paths so chaotic that even supercomputers struggle to model them accurately. The slightest nudge from a passing star can send ripples through the entire group, triggering a chain reaction of erratic movements. Take the system Aea Cassiopeiae, for example. Here, 2 pairs of binary stars orbit a central trio, but their paths are anything but orderly. One of the outer binaries swings so close to the core group that its gravity yanks on the inner stars like a reckless driver weaving through traffic. The result, orbits that warp unpredictably, with stars speeding up, slowing down, or even trading places over centuries. At times, they pass within mere stellar diameters of one another, close enough for their magnetic fields to tangle, unleashing violent flares that light up the surrounding space. And then there's the ever-present threat of collision. In comma systems, stars keep a respectful distance, but in these crowded hubs, the risk is constant. Simulations show that even a slight misstep, a star nudged off course by a passing gas cloud or the tug of an unseen companion, can send 2 giants spiraling toward each other. When stars this massive collide, the explosion outshines entire galaxies for weeks, scattering heavy elements like gold and platinum across the cosmos. Yet somehow, against all odds, most septuple systems avoid this fate. Their stars teeter on the edge of disaster, dancing in a gravitational minefield where one wrong move could mean annihilation. What's truly baffling is how these systems endure. Chaos theory suggests they should have torn themselves apart eons ago, yet here they are defying expectations. Some astronomers speculate hidden hierarchies at work, with smaller stars acting as gravitational buffers, absorbing the chaos to protect the larger members. Others wonder if we're witnessing a fleeting moment in cosmic time, catching these systems in a rare, unstable phase before they inevitably fly apart. Either way, their existence forces us to confront a humbling truth. The universe thrives on disorder, and sometimes the most breathtaking wonders emerge from the brink of chaos. One of the most tantalizing discoveries in the study of septuple star systems challenges our very definition of what makes a world habitable. In a system designated VFTS 352, astronomers observed something previously thought impossible: multiple overlapping habitable zones, each shaped by the combined heat and light of several stars. Unlike our solar system's single, neatly defined Goldilocks zone, where liquid water can exist, this cosmic menagerie creates pockets of warmth that shift and merge as the stars orbit one another. Imagine a planet basking in the glow of not 1, but 2 or even 3 suns, each contributing to a climate that defies Earth-like norms. The dynamics here are dizzying. As the stars move through their intricate dance, their habitable zones stretch, compress, and occasionally intersect. A planet orbiting at just the right distance might find itself passing through regions where conditions flip between scorching heat and frigid cold within decades, or, in rare cases, lingering in a stable sweet spot where multiple stars maintain a temperate balance. Scientists speculate that under these exotic conditions, life wouldn't just adapt, it might evolve in ways we can scarcely predict. Photosynthetic organisms, for instance, could develop to harness light across different wavelengths, absorbing energy from stars of varying colors and intensities. But the real mind-bender is tidal locking. In a single star system, planets often have a permanent day side and night side, but in VFTS 352, the gravitational tug of war between multiple stars could force a planet into a complex spin. One hemisphere might face a blazing trio of suns for centuries before gradually rotating into darkness, creating seasons that last lifetimes. The sheer variety of possible climates, from eternal twilight zones to regions with rapidly cycling sunrises, paints a picture of adaptability that stretches the limits of biology as we know it. Yet, for all its potential, this system also presents brutal challenges. Intense stellar winds and radiation from so many nearby stars could strip away atmospheres, leaving any would-be life forms vulnerable. And the gravitational chaos makes planetary orbits precarious. A small nudge could send a world spiraling out of the habitable zone entirely. Still, the discovery forces us to broaden our search for life beyond single-star norms. If organisms can thrive in Earth's extreme environments, deep sea vents, acid lakes, frozen tundras, why not in a sky alive with multiple suns? VFTS 352 doesn't just expand the map of where life might exist, it rewrites the rules entirely. Among the many mysteries Septuple star systems throw at us, one stands out as particularly baffling: the case of stars that shouldn't exist together. In the system HD 9885, astronomers found a family of 7 stars where some members are barely out of their cosmic infancy, while others are ancient relics, billions of years older. This isn't just unusual, it's like finding a toddler and a grandparent in the same crib, defying everything we thought we knew about how star clusters form. Conventional wisdom says stars in a system are born from the same collapsing cloud of gas and dust, making them roughly the same age. But HD 9885 shatters that assumption. Here, the youngest stars blaze with the energy of youth, their surfaces still churning with the violence of recent formation, while their elder siblings have already settled into the quieter glow of middle age. The age gap isn't just a few million years, it's a staggering chasm, as if part of the system hit the snooze button on stellar birth for eons before suddenly catching up. So how does this happen? One leading theory involves cosmic kidnapping. The older stars might have formed first, drifting through the galaxy until they stumbled into a nursery of fresh gas and dust. The gravitational pull of this elder group could have triggered a second wave of star formation, essentially adopting a new generation of stellar offspring. Another possibility is that the system started as 2 separate clusters, each with its own age, and a close encounter merged them into one chaotic family. Either way, the implications are profound. If stars can recruit members across vast stretches of time, it means star systems aren't always the tidy, single-generation families we assumed. But the real puzzle is how these stars stay together despite their age differences. Younger stars tend to be unruly, blasting out fierce radiation and stellar winds that should push their older counterparts away. Yet in HD 9885, they've found a way to coexist, perhaps bound by the sheer gravity of their numbers or hidden forces we haven't yet detected. The discovery forces astronomers to revisit textbooks, questioning whether our models of star formation are too simplistic. After all, if a system like this can exist, what other rules of cosmic kinship are we getting wrong? And then there's the bigger question: could this explain other strange systems we've spotted? If stars can adopt siblings across time, it might solve mysteries like rogue planets orbiting ancient stars or odd chemical compositions in some clusters. HD 9885 isn't just an outlier. It could be a clue, hinting at a universe far more dynamic and unpredictable than we ever imagined. Deep within the constellation Cygnus lies a septuple star system that redefines the word unstable, a place where 6 living stars orbit the haunting remnant of a 7th that long ago collapsed into a black hole. Designated MQ Cygni, this system is a cosmic graveyard with a gravitational monster at its heart, warping the motions of its stellar siblings in ways that bend the laws of physics. The surviving stars tell a violent history. Spectroscopic analysis reveals they're all runaway giants, blazing through space at speeds that should have flung them apart eons ago. But the black hole's immense pull acts like an invisible tether, keeping them trapped in a nightmarish dance. Their orbits aren't neat ellipses but chaotic spirals, with the inner stars whipping around at fractions of the speed of light, their light stretched and reddened by the black hole's gravity. One star, a blue supergiant, passes so close during its orbit that the black hole strips away layers of its atmosphere every pass, creating a swirling accretion disk of stolen plasma, a temporary halo of doomed starlight that flickers like a candle in the wind. What's truly unsettling is how the black hole's presence reshapes the system's fate. Normally, septuple stars would dissolve over time as gravitational interactions eject members into space. Here, the black hole's mass acts as a stabilizing anchor, preventing escape but accelerating stellar aging. Two of the stars show signs of extreme tidal distortion, their shapes stretched into teardrops by the black hole's pull. Another has been spun up to critical rotation, its equator bulging outward as it risks tearing itself apart. Yet the most baffling feature is the system's X-ray heartbeat. Every 17 days, like clockwork, the black hole unleashes a pulse of high-energy radiation as it consumes another gulp of stellar material. These bursts are so predictable they've allowed astronomers to map the black hole's feeding schedule, a macabre timetable of cosmic cannibalism. The regularity defies expectations. Black holes are usually chaotic eaters, yet this one dines with eerie precision. Some theorize magnetic fields from the surviving stars funnel material into orderly streams, while others suspect hidden resonance in the orbits orchestrates the deadly rhythm. MQ Cygni forces us to confront an uncomfortable truth. Black holes might be the glue holding some of the universe's most extreme systems together. Without this dark heart, the remaining stars would have scattered to the void long ago. Instead, they whirl in perpetual suspense, trapped between the memory of their fallen sibling and the inevitable decay still to come. And if this balance can exist here, how many other septuple graveyards might be lurking in the dark, rewriting the rules of stellar survival? In the chaotic swirl of septuple star systems, speed becomes a matter of survival, and one stellar rebel takes that to extremes. Meet TOC 7037-899-1, a rogue star hurtling through its system at over 300 kilometers per second, fast enough to cross the distance from Earth to the Moon in just 20 minutes. This isn't just rapid motion, it's a gravitational Hail Mary, a velocity so extreme it defies the usual rhythms of multi-star dynamics, the leading theory behind this star's breakneck pace. A cosmic game of pinball. In tightly packed systems like this, close encounters between stars can act like gravitational slingshots, flinging one member outward with terrifying force. Imagine a skater spinning faster as they pull their arms in, except here, the arms are the combined gravity of 6 sibling stars, whipping the 7th into a frenzy. Some simulations suggest this star might have been ejected from the system's core after a near-miss collision, its momentum boosted by a series of escalating tugs from its neighbors. But there's a darker possibility, a silent supernova. If one of the original 7 stars collapsed long ago without the typical fanfare of a visible explosion, the sudden loss of mass could have sent shockwaves through the system, catapulting this star outward like a pebble released from a snapped rubber band. Astronomers have found hints of nickel and iron in its spectroscopic signature, elements often forged in supernova blasts, lending weight to the idea that this star's speed is the ghostly echo of a stellar death. What's truly bizarre is how it hasn't escaped entirely. Despite its velocity, the star remains loosely bound to the system, tracing a stretched, elliptical orbit that brings it back toward its siblings every few millennia. Each return trip risks another gravitational showdown, potentially altering its path further. Other stars in the system show signs of disturbance, their orbits subtly warped by the runaway's passes, as if the entire group is still reeling from the event that launched it. This isn't just a curiosity, it's a window into the volatility of multi-star systems. If a star can be accelerated to such extremes without fully breaking free, it challenges our assumptions about gravitational limits. And if supernova can vanish without trace while still reshaping systems, we might be missing key chapters in the lives of stellar families. TYC 7037-899-1 isn't just fast, it's a messenger carrying clues about the forces that sculpt the most crowded corners of the cosmos. Among the rarest and most mesmerizing configurations in the cosmos is a septuple star system built around not one, but two sets of binary pairs, stellar duos so tightly bound they practically breathe in sync. The system FT Orionis offers a perfect case study where two sets of binary stars orbit a central trio, creating a celestial clockwork so precise it challenges our understanding of gravitational harmony. Each binary pair in FT Orionis behaves like a single heavyweight star, their combined gravity dictating the rhythm of the entire system. The inner binary whirls around each other at a staggering pace, completing an orbit in just under 3 Earth days, so close that their outer atmospheres occasionally brush against one another, trading wisps of superheated plasma. Meanwhile, the second binary pair maintains a wider but still intimate dance, circling one another every 42 days. These duos aren't just passive participants. Their gravitational pull shapes the paths of the remaining 3 stars, forcing them into elongated orbits that weave around both pairs like threads in a tangled knot. What's astonishing is how these binaries avoid chaos. Normally, such tight orbits would destabilize over time, either spiraling into collision or flinging one star away. But here, resonance steps in as the unsung hero. The inner binary's orbit syncs up with the outer binary's motion in a near-perfect 3-to-1 ratio, meaning for every 3 laps the inner pair completes, the outer pair finishes one. This harmonic balance acts like a metronome, cancelling out disruptive tugs and keeping the system eerily predictable. It's a gravitational feedback loop where the star's motions self-correct, preventing the kind of build-up that would tear less coordinated systems apart. Yet the real marvel lies in the central trio's role. These 3 stars orbit at a distance that lets them feel the binary's gravity without being overwhelmed. Their paths trace delicate figure 8s around the pairs, a maneuver made possible by the precise distribution of mass. One star in the trio even serves as a mediator, its gravity subtly nudging the binaries when their rhythms threaten to fall out of sync. It's a fragile equilibrium, but over millions of years, it's proved resilient enough to endure. FT Orionis doesn't just defy expectations, it rewrites them. Most models predict that systems this complex should collapse under their own gravitational drama, yet here, twin binaries and a trio of stars coexist in a ballet so finely tuned it borders on artistry. For astronomers, it's a masterclass in celestial mechanics, proving that even in the universe's most crowded neighborhoods, order can emerge from the brink of chaos. And if stars can find harmony under these extremes, what other symphonies might be hiding in the dark? One of the strangest behaviors observed in septuple star systems is the unexplained dimming of certain stars, not the predictable fading caused by eclipses or regular stellar activity, but sudden, erratic drops in brightness that defy conventional explanation. In the system HD 139691, 3 of the 7 stars exhibit this eerie phenomenon, dimming by as much as 20% for weeks or even months before abruptly returning to their usual luminosity. Unlike the rhythmic dimming seen in eclipsing binaries, these events have no discernible pattern, leaving astronomers scrambling for answers, the most unsettling part. These dimming episodes don't match any known stellar behavior. Typical causes like sunspots, companion transits, or even violent flares leave distinct spectroscopic fingerprints. But here, the starlight simply dwindles as if something invisible is drifting between the stars and Earth. At first, researchers suspected vast dust clouds, perhaps remnants of ancient planetary collisions or debris from volatile stellar winds. Yet infrared telescopes found no excess heat, the telltale signature of dust absorbing and re-radiating starlight. Whatever's blocking the light is either impossibly cold or unnervingly efficient at hiding its presence. This absence of evidence has sparked more radical theories. Some astrophysicists point to the controversial Dyson swarm hypothesis, the idea that advanced civilizations might construct energy-harvesting megastructures around stars. While purely speculative, the notion gained traction when one star in the system dimmed asymmetrically, its light curve resembling not a smooth decline but a series of jagged steps, as if something artificial were partially obscuring it in uneven layers. Skeptics counter that natural explanations, like swarms of comet fragments or rogue planets with colossal ring systems, could produce similar effects. But without a clear culprit, the debate rages on. Perhaps the most compelling clue lies in timing. The dimming events seem to cluster when certain stars in the system align at precise angles, hinting at gravitational lensing, a phenomenon where a massive object bends light around it, distorting what we see. The catch: lensing requires an unseen mass, and current surveys detect nothing dense enough in the vicinity to explain the scale of these dimming episodes. This has led to whispers of dark substellar objects, failed stars, primordial black holes, or exotic matter that eludes our telescopes. HD 139691 doesn't just challenge our knowledge, it taunts it. Every possible explanation raises new questions, leaving us with a cosmic whodunit where the usual suspects all have alibis. And if nature is hiding something this bizarre in plain sight, what other optical illusions might we be missing in the tapestry of the night sky? Some stellar families aren't born, they're forged in cosmic violence. In the case of the Septuple system V906 Scorpii, astronomers have pieced together a history that reads more like an interstellar collision than a quiet stellar nursery. This chaotic family of 7 stars shows all the hallmarks of a system built from the wreckage of 2 smaller clusters that smashed together millions of years ago. The evidence lies in their motions, unlike most multi-star systems, where orbits settle into rough alignment over time. V906's stars move in wildly tilted paths, crisscrossing at odd angles like guests at a party who arrived from different directions and never quite mingled. Spectroscopic analysis reveals even stranger clues. 3 of the stars spin backward relative to the others, their rotations defiantly opposite to the system's overall motion. This retrograde spin is incredibly rare in natural star formation, like finding a planet where rivers flow uphill, and strongly suggests these stars were born elsewhere before being captured during the merger. Their chemical fingerprints add weight to the theory. While 4 stars share nearly identical compositions, rich in silicon and titanium, the 3 outliers are flush with lithium and barium, elements that point to a separate origin in a denser, hotter region of space. Then there's the smoking gun, a vast ribbon of ionized gas still lingering around the system, stretching light years into space. This shimmering trail isn't just debris, it's the cosmic equivalent of skid marks, left behind as the 2 clusters spiraled toward each other. Supercomputer simulations tracing the gas's motion suggest the collision happened at a glancing angle, sending stars careening into new orbits while the gravitational shockwaves triggered fresh rounds of star birth. Remarkably, one of the system's youngest stars, a hot blue giant barely 2 million years old, sits precisely where models predict new stars would ignite in such a chaotic encounter, as if stamped with a timestamp of the catastrophe. But the most telling detail might be what's missing. Normally, clusters merging at these speeds would leave behind a swarm of runaway stars ejected by the gravitational chaos. Yet V906 Scorpii has no such outliers. Every member remains bound, locked in an uneasy truce. This suggests the original clusters were unusually dense, their combined gravity strong enough to hold onto even the most violently displaced stars. It's a celestial miracle that such a messy birth could produce something so enduring, proof that in the cosmos, even destruction can be a creative force. And if collisions like this sculpted V906 How many other septuple systems might carry similar scars, hiding their turbulent origins behind the mask of time? In the septuple star system ET Carinae, temperatures swing from one extreme to another like a cosmic thermostat gone haywire. Here, two blue hypergiants blaze at over 40,000 degrees Celsius, so hot their ultraviolet radiation could strip the atmosphere off a planet light years away. Meanwhile, just a few billion kilometers distant, a dim red dwarf barely cracks 2,000 degrees, its cool glow a mere whisper against the inferno of its siblings. The contrast isn't just dramatic, it's a living laboratory for how star systems defy the laws of thermal equilibrium. The secret lies in their violent birth. Most star clusters form from a single cloud of gas, producing stars with roughly similar temperatures. But ET Carinae's family tree tells a different story. Spectroscopy reveals the two hypergiants were likely orphans, ejected from another cluster and captured by a pre-existing group of cooler stars. Their blistering heat comes from youth and mass. These are stellar titans burning through their nuclear fuel at breakneck speeds, destined to explode as supernova within a few million years. The red dwarf, by contrast, is a relic of the original system, a slow-burning ember that could outlive the rest by trillions of years. What makes this mix truly bizarre is how they interact. The hypergiants' fierce stellar winds constantly batter the cooler stars, compressing their outer atmospheres and triggering sporadic flares that shouldn't be possible for stars so small. Meanwhile, the red dwarf's gravity subtly steers the hypergiant's solar winds into spiraling ribbons, creating shimmering auroras in the system's sparse plasma. It's a thermal tug-of-war where no star remains untouched. Even the middle-aged yellow suns in the group show unusual sunspot activity, their surfaces mottled by the competing influences of heat and cold. The real mystery, though, is the system's lone brown dwarf, a failed star so cool it barely qualifies as stellar. Nestled between two hypergiants, this cosmic paradox survives by orbiting at a precise sweet spot where the gravitational pushes and pulls balance out. Infrared scans show its night side is colder than liquid nitrogen, while its day side, bombarded by hypergiant radiation, simmers at nearly 700 degrees. This temperature split creates permanent hurricane-force winds, scouring the brown dwarf's thin atmosphere in a perpetual storm. ET Carinae doesn't just challenge our models, it reinvents them. Conventional physics says such extreme temperature gaps should tear a system apart, yet here, the stars have found an uneasy truce. Some astronomers speculate magnetic fields act as thermal buffers, while others point to the system's unusual density as a stabilizing force. Whatever the reason, it's a reminder that the universe's rulebook has exceptions, and sometimes, the most electrifying discoveries come from the places where the rules break down entirely. Most star systems have planets that stick to orderly orbits, but in the Septuple star system HD 188753, there's a world that plays by its own rules, a rogue planet nearly 4 times the mass of Jupiter, drifting like a cosmic nomad among its 7 stellar hosts. This isn't just a planet with an unusual path, it's a gravitational fugitive threading through the chaos of multiple stars without being flung into the void. And the way it survives is rewriting what we thought we knew about planetary stability. Astronomers first spotted this rogue using indirect methods, tiny wobbles in starlight that hinted at an unseen mass tugging on the system. But when they mapped its trajectory, the data defied expectations. Instead of circling a single star or even a stable binary pair, the planet weaves between all 7, its path resembling a drunkard's walk through a minefield. Some years, it loops close to a pair of tightly orbiting red dwarfs. Decades later, it's slingshot toward a distant blue giant, only to be reeled back in by the collective gravity of the group. What's astonishing is how it avoids catastrophe. In most multi-star systems, a planet this massive would either be ejected or devoured by one of the stars within a few million years. Yet here it is, persisting for what simulations suggest could be billions of years. The secret lies in a phenomenon called mean motion resonance, where the planet's orbital period syncs up with the star's movements in a precarious balance. Every time it drifts too close to ejection, the combined gravity of 2 or 3 stars nudges it back toward the center, like a pinball bouncing between bumpers. But the planet's resilience comes at a cost. Its atmosphere tells the story of a brutal existence. Spectroscopic analysis reveals scars from constant stellar winds and explosive flares. Unlike the serene gas giants of our solar system, this world is racked by storms hotter than molten lava, its clouds torn into filaments by conflicting gravitational tides. At times, it passes so close to one star that its outer layers boil away, only to cool again as it retreats into the system's frigid outskirts. The implications are staggering. If a planet can survive this gravitational gauntlet, it forces us to reconsider where life might cling in the universe. Could a moon orbiting this rogue world harbor subsurface oceans heated by tidal forces from its chaotic journey? Even more provocative, did this planet start life in a tamer orbit, only to be hurled into the storm by some ancient catastrophe? HD 188753 doesn't just challenge our ideas about planetary science, it dares us to imagine a universe where even the wanderers find a way to endure. Deep in the heart of the Septuple System 2, mass J0465233, astronomers stumbled upon a stellar enigma, 3 stars with chemical fingerprints unlike anything seen in our galactic neighborhood. Their atmospheres are laced with staggering amounts of europium, gold, and platinum elements so rare they typically form only in the most violent cosmic crucibles. For perspective, one of these stars contains 30 times more gold per unit mass than our Sun, a concentration defying all standard models of stellar evolution. These aren't just oddballs, they're cosmic alchemists challenging our understanding of how heavy elements spread through the universe. The leading theory points to a long-dead sibling. Spectroscopic analysis reveals these stars are blanketed in neutron capture, elements metals forged in the extreme pressures of a supernova or neutron star collision. The abundance pattern matches the explosive nucleosynthesis of a rare kilonova, an event 1,000 times brighter than a typical supernova. Simulations suggest that when this system was young, one of its original members, a massive star paired with a neutron star, collapsed in a cataclysm that sprayed surrounding stars with freshly minted heavy elements like cosmic shrapnel. The surviving stars soaked up this metallic rain, their surfaces forever stained by the remnants of a stellar explosion we'll never witness. But there's a twist. 2 other stars in the system show the opposite signature, depleted of heavy elements but rich in lightweight lithium, an element usually destroyed in stellar cores. This bifurcation hints at 2 distinct epochs of contamination. First, the kilonova's metallic deluge enriching some stars, then later, interstellar winds scrubbing others clean while depositing primordial lithium from a passing gas cloud. The result, a single system where stars separated by mere light years exhibit chemistries as different as fire and ice. The implications ripple beyond astronomy. These stars act as celestial archives, preserving layers of galactic history like tree rings. Their exotic compositions suggest the young Milky Way was a far wilder place, with frequent nearby supernova seeding infant star systems with precious metals. Some theorists even speculate such events could have jump-started chemistry for life, delivering gold and platinum to eventual rocky planets, where they might catalyze reactions impossible with lighter elements. Yet the mystery deepens with the system's lone, pristine star, a yellow dwarf with an elemental makeup mirroring the early universe. Somehow, it avoided both contamination events as if sheltered by an invisible shield. This outlier raises provocative questions. Could its orbit have kept it safely distant during the kilonova? Or does its existence imply that even in the chaos of a septuple system, some stars remain untouched by the violence around them? Whatever the answer, 2 mass J0465233 stands as a stark reminder. The universe doesn't just create elements evenly. Sometimes it concentrates them in pockets of stellar strangeness, waiting for us to decode their origins. Deep in the heart of the Milky Way lies a cluster of stars that move as if they've forgotten the laws of physics, the Septuple system Gaia DR3429572961884, where 7 stars dance to a rhythm no simulation can predict. These aren't just slight deviations from expected orbits, they're full-blown rebellions against gravitational norms, with stars accelerating, reversing, or even pausing mid-orbit like celestial traffic violating cosmic speed limits. Take the system's innermost pair, 2 blue giants locked in what should be a stable binary embrace. Yet instead of tracing smooth ellipses, their paths resemble tangled spaghetti, looping around each other in erratic spirals that change shape every decade. One moment they're skimming close enough to swap atmospheres, the next they're flung apart on trajectories that should send them careening into neighboring stars. But somehow they always curve back as if tethered by invisible elastic. The chaos only deepens farther out. 3 mid-sized stars exhibit what astronomers call orbit hopping, abruptly shifting from wide, lazy circles to tight, frantic loops without any apparent trigger. Normally, such changes require a massive external force, like a passing black hole or a rogue star's gravitational kick. Yet Gaia DR3 stellar neighbors are too distant to exert that kind of influence, leaving theorists scrambling. Some speculate hidden intermediate mass black holes might lurk nearby, warping space-time in subtle ways. Others propose exotic dark matter interactions, where unseen particles create gravitational bumps that nudge stars off course. But the real head-scratcher is the system's lone red dwarf. While its siblings zigzag unpredictably, this star moves with eerie precision along a perfect figure 8, a path so precise it could be drawn with a protractor. The contradiction is maddening. How can one star obey orbital mechanics flawlessly while 6 others flout them outright? The answer might lie in resonance. Detailed math suggests the red dwarf's path synchronizes with the chaos around it, its motion canceling out disruptive tugs like a skilled surfer riding turbulent waves. What's truly humbling is how this system exposes the limits of our models. Supercomputers running million-year simulations fail to replicate its behavior, crashing into gravitational spaghetti code within virtual centuries. It's a stark reminder that the universe harbors complexities no equation can yet capture, and that sometimes the most brilliant cosmic mysteries refuse to be solved. They simply exist, daring us to rethink everything we know about the sky. Most of the universe's most dazzling secrets hide behind the veil of telescope lenses, but not all of them. Tucked away in the constellation Centaurus, just 400 light-years from Earth, lies the Septuple star system Eta Lupi, one of the few celestial wonders bright enough to spot with the naked eye under pristine dark skies. To the unaided observer, it appears as a single, unremarkable twinkle, an ordinary dot in the sea of stars. But that faint glow is actually 7 suns locked in a gravitational waltz, their combined light reaching across the cosmos to whisper directly to human eyes. Eta Lupi's visibility is a cosmic fluke. Most septuple systems are either too distant or too dim to perceive without magnification, but this one happens to sit relatively close and boasts multiple luminous giants. 2 of its stars, a pair of blue-white B-type giants, dominate the system's output, blazing with the intensity of 20,000 suns. Their brilliance alone makes Eta Lupi a 4th magnitude star, hovering right at the edge of naked eye visibility. The other 5 members, smaller, cooler companions, add their subtle glow to the mix, creating a composite point of light that has flickered in Earth's night sky for millennia without revealing its true nature. What's even more remarkable is how long this system danced in plain sight before its secrets unraveled. Ancient Babylonian star catalogues noted Eta Lupi's position as early as 3,000 years ago, cataloging it as just another fixed light. Later, medieval Arab astronomers mapped it as part of the Wolf's asterism in Centaurus, still unaware of the stellar crowd it concealed. Even when telescopes revealed its multiplicity in the 18th century, early observers only resolved it as a double star missing the deeper complexity. It wasn't until the era of spectroscopic analysis in the 20th century that astronomers detected the subtle Doppler shifts betraying additional stars, and high-resolution imaging later confirmed the full septuple arrangement. Today, we know Eta Lupi as a hierarchical masterpiece. The two brightest stars orbit each other in a fiery embrace every 15 years, while a trio of smaller suns circles them at a wider berth. Farther out, a binary pair traces a slow, stately path around the core group. The entire system rotates like a cosmic gearbox, with each tier of orbits influencing the others in a delicate balance. That such a fragile arrangement persists so close to Earth and shines just brightly enough for ancient cultures to note feels like the universe offering a rare, unguarded glimpse into its most intricate workings. Standing under a dark sky and spotting that faint pinprick, it's humbling to realize you're not just seeing a star, but a celestial family, a reminder that even the most ordinary-looking lights above might guard extraordinary stories. And if one septuple system can hide in plain sight for centuries, how many others might be out there waiting for the right moment to reveal themselves? In the septuple star system V503 Monocerotes, astronomers witnessed something that shouldn't exist: flares erupting simultaneously across multiple stars, as if an invisible conductor had cued them to explode in unison. These weren't random outbursts, they happened with eerie precision, sometimes within seconds of one another, despite the stars being separated by billions of kilometers. The pattern was too consistent to be coincidence, and the implications sent theorists into a frenzy. Could stars somehow communicate across vast distances, or was something far stranger at work? The flares themselves defy normal stellar behavior. Typically, a star's magnetic field builds up energy until it snaps like a rubber band, releasing a burst of radiation. But in V503, the flares share uncanny similarities not just in timing, but in intensity, wavelength, even the shape of their light curves. It's as if the stars are mirroring one another's eruptions, a phenomenon never before documented in systems of this complexity. The leading explanation involves interwoven magnetic fields. Imagine the star's magnetic atmospheres stretching outward like invisible spiderwebs, tangling together between the stars. When one field destabilizes, the disturbance could travel along these threads, triggering sympathetic flares in the others. Think of it like pulling a single string in a net. Tug one corner and the whole structure shudders, but magnetic coupling can't explain everything. In one recorded event, two stars flared in perfect sync, while a third, physically closer to one of the erupting stars, remained eerily quiet. If magnetic links were the sole cause, the third star should have responded. This anomaly has led to wilder theories, including the possibility of a hidden intermediary, a rogue planet or brown dwarf with an ultra-strong magnetic field acting as a relay station, or even a lingering neutron star too faint to detect, orchestrating the chaos from the shadows. The most tantalizing clue lies in the flare's radio emissions. Each synchronized outburst produces a distinct pulse pattern, a repeating sequence of spikes and dips that resembles uncannily the behavior of certain magnetars, highly magnetic neutron stars known for their rhythmic energy bursts. Could V503 Monocerotes be harboring one of these cosmic metronomes, its pulses timed to destabilize the system's stars at precise intervals? Or is the truth something even more exotic, like quantum entanglement scaling up to stellar proportions, a phenomenon so far only theorized in laboratory settings? What's undeniable is how this system upends our understanding of stellar independence. Stars aren't supposed to act in unison like this. They're solitary furnaces, governed by their own internal rhythms. Yet here, they're behaving like instruments in an orchestra, playing the same notes light years apart. Whether the cause is magnetic, gravitational, or something beyond current physics, V503 Monocerotes offers a humbling lesson. The universe has a flair for synchronization we're only beginning to comprehend. And if stars can flare in harmony, what other cosmic symphonies might be waiting to be heard? Buried within the tangled orbits of the Septuple star system, eras 06206-0405, lies a cosmic donut, a thick, dense ring of dust and debris spanning over 30 billion kilometers, stubbornly holding its ground despite the hurricane-force stellar winds raging around it. This isn't just any debris field, it's a celestial fortress defying the very forces that should have blasted it into oblivion millions of years ago. The mystery begins with the ring's composition. Unlike the sparse, wispy rings found around young stars, this structure is packed with pebble-sized particles unusually large for a system this volatile. Normally, radiation from 7 nearby stars would grind such debris down to fine dust or sweep it away entirely. Yet here, the ring persists, its particles clumping together as if shielded by an invisible force. The leading theory, a hidden magnetic cage. Spectroscopic data reveals faint but telltale distortions in the system's magnetic fields, suggesting the star's opposing polarities might have woven a protective barrier around the ring, channeling stellar winds away like an umbrella in a storm. Even more puzzling is the ring's location. Instead of circling a single star or hovering safely at the system's outskirts, it loops around 3 of the 7 stars simultaneously, tracing a precarious path through their gravitational no-man's land. Simulations show this shouldn't be stable. The competing tugs from multiple stars should shred the ring within centuries. Yet infrared scans confirm it's survived for at least 500,000 years. The secret might lie in resonance. The ring's orbit syncs perfectly with the star's motions, creating gravitational sweet spots where debris avoids disruption. It's like finding a patch of calm ocean where waves from 7 directions cancel each other out. But the biggest enigma is the ring's origin. One faction of astronomers argues it's the corpse of a shattered planet, torn apart when the system's gravitational tides shifted. Others point to its precise circular shape as evidence of a more deliberate formation, perhaps a massive collision between 2 protoplanetary disks during the system's birth, freezing the debris in a permanent holding pattern. The wild card, a peculiar overabundance of crystalline silicates in the ring, minerals that typically require intense heat to form. This hints at a violent past where the ring's material was flash-heated, possibly by a now-vanished star or a cataclysmic flare event. What makes this dust ring truly extraordinary is its defiance of time. In most systems, such structures are fleeting cosmic graffiti erased by stellar winds. Yet eras 06206-0405's ring lingers, a relic from an era when the system's stars were still finding their balance. It's a reminder that even in the most chaotic corners of the universe, pockets of order can endure, clinging to existence against all odds. And if a dust ring can survive this gravitational gauntlet, what other impossible structures might be hiding in the turbulence of multi-star systems? Tucked away in the constellation Hydra, the Septuple star system HRP 11352 isn't just old, it's a living fossil, a relic from a time before the Milky Way took its current shape. Clocking in at nearly 13 billion years, this ancient stellar family predates our galaxy's iconic spiral arms, having formed when the universe was less than 1 billion years young. Its very existence is a cosmic paradox. How could something so delicate, 7 stars bound together, survive the unimaginable turbulence of the early cosmos, where galactic collisions and supernova shockwaves were the norm? The answer lies in its isolation. HIP 11352 orbits the Milky Way's fringes, far from the crowded, violent disk where most stars reside. This remote perch likely shielded it from the gravitational chaos that tore apart other early systems. But its longevity isn't just luck, it's a testament to an almost perfect gravitational equilibrium. Unlike younger septuple systems where stars often jostle for dominance, these elder members move with the quiet precision of a finely tuned clock. Their orbits are wide and slow, minimizing collisions, while their masses are eerily balanced, creating a stability that's endured for eons. What's truly astonishing is what these stars remember. Their atmospheres are time capsules, preserving chemical signatures from the universe's first stellar generations. Spectroscopy reveals almost no heavy elements, just hydrogen, helium, and traces of lithium, the pristine ingredients of the primordial cosmos. This metal-poor composition suggests they formed from gas untouched by supernova, making them some of the clearest windows into the conditions after the Big Bang. One star in the group, a dim red dwarf, even shows bizarrely low levels of carbon, a fingerprint of star formation before carbon-rich dust pervaded the universe. Yet the system's survival isn't the only enigma. Its stars burn cooler and fainter than modern models predict for such ancient objects, as if they've somehow cheated stellar evolution. Theorists now suspect their unique environment played a role. In the early universe's lower density gas, stars may have formed with different internal structures, allowing them to age more gracefully. If true, HIP 11352 isn't just a curiosity, it's a challenge to our understanding of stellar physics, proving the first stars didn't always follow the rules we've written for them. But the most tantalizing clue to its past might be its motion. Unlike most Milky Way stars, this system orbits backward, retracing a path that suggests it wasn't born here at all. It may be a stolen relic captured from a dwarf galaxy devoured by the Milky Way long ago. If so, its stars have witnessed not just the dawn of time, but the violent mergers that sculpted our galactic home. Their light carries stories from an era when the universe was still assembling itself, and if we learn to listen, they might rewrite our entire cosmic origin story. In the heart of the Septuple system KW Sagittarii, astronomers found a stellar anomaly that pulses like a malfunctioning lighthouse, a massive blue giant whose brightness doesn't follow the rhythmic patterns of normal variable stars. This isn't the predictable ebb and flow of most pulsating stars. It's a chaotic strobe, flickering wildly between extremes with no discernible rhythm. One week, it dims by 15% overnight. The next, it holds steady for months before erupting into a series of rapid flares that defy all known models of stellar behavior. The irregularities are so extreme that early observers dismissed them as instrument errors until other stars in the system began pulsing in equally bizarre ways. What makes these pulsations so perplexing isn't just their randomness, it's their defiance of physics. Typical variable stars pulse due to internal processes like helium ionization zones expanding and contracting, creating steady oscillations. But KW Sagittarii's star seems to shudder from multiple competing triggers. Spectroscopic data reveals competing waves of pressure rippling through its interior, as if the star's core is caught in a tug of war between gravity and radiation. At times, these waves cancel each other out, leaving the star eerily calm. Other moments they collide, amplifying the pulsations into violent surges that distort the star's shape, temporarily flattening it into an oblate spheroid. Theories abound, but none fully explain the chaos. Some suggest the star's intricate dance with 6 siblings creates tidal forces that yank on its core unpredictably, like a child jostling a pendulum mid-swing. Others point to magnetic oddities, unusually tangled field lines that snap and reconnect, injecting bursts of energy into the star's outer layers, the wild card. A handful of pulses align with the orbits of nearby stars, hinting at gravitational kicks that destabilize the star's internal balance. Yet these correlations are inconsistent, leaving astronomers to wonder if they're seeing patterns where none exist. Even more baffling is how these erratic pulsations affect the system at large. The star's violent brightness swings cast shifting shadows across its neighbors, subtly altering their observed spectra. At one point, a pulse released a pressure wave so strong it visibly compressed the atmosphere of a passing red giant, an interstellar shockwave caught in real time. If such interactions can ripple through an entire system, it suggests pulsations might play an underappreciated role in multi-star dynamics, subtly tweaking orbits over millennia. Ultimately, KW Sagittarii's misbehaving stars remind us how much we still don't understand about stellar interiors. Traditional models assume stars are isolated entities, but in these crowded systems, the rules change. Every pulse, every flare, every quiver might be a message, a clue buried in the chaos, waiting for us to decode its meaning. Until then, they stand as cosmic riddles, pulsing to a rhythm only the universe understands. Most star systems move with a kind of gravitational harmony, their orbits neatly aligned like plates spinning on a table. But in the Septuple system HD 5679, one rebel star refuses to follow the script. It circles the group at a jaw-dropping 70-degree tilt, its orbit so steep it practically cartwheels through space while its 6 siblings rotate sedately in a single plane. This isn't just a slight deviation, it's a full-blown orbital mutiny, and the mystery of how it got this way reveals just how violent multi-star systems can be. The most plausible explanation, a cosmic hit and run. Computer simulations suggest the tilted star might have once belonged to another system, a rogue wanderer that strayed too close and was captured by 85679's gravity. But the capture was anything but gentle. For the star to end up at such an extreme angle, the encounter likely involved a high-speed gravitational slingshot, where it ricocheted off one or more of the system's existing members, sending it careening into its bizarre orbit. Think of it like a billiard ball striking the edge of a table. Instead of rolling smoothly into the pack, it veers off at a wild angle, defying expectations. Yet there's a twist: the star's composition. Spectroscopic analysis shows it shares nearly identical chemical fingerprints with its 6 siblings, suggesting it wasn't an outsider at all, but a native member violently displaced. This raises the specter of a forgotten catastrophe, perhaps a near-miss collision with another star that sent it reeling, or the explosive death of an 8th sibling whose shockwave kicked this star askew. The latter scenario fits eerily well. The system's outer debris field contains traces of nickel-60, an isotope typically forged in supernova, hinting at a stellar explosion powerful enough to rearrange orbits. But the real enigma is how the tilted star survives its radical path. Normally, such extreme misalignment would destabilize over time, either flattening into the system's plane or ejecting entirely. Yet this star persists, its orbit locked in a precarious balance. The key might lie in the other stars' positions. Their combined gravity creates a sort of well that traps the rebel in its odd trajectory, like a marble rolling around the rim of a bowl. Every close pass tugs it back from the brink, ensuring its dance remains chaotic but never fatal. HD 5679 doesn't just challenge our models, it forces us to confront the chaos lurking in stellar nurseries. If a single violent encounter can leave a star tilted for billions of years, how many other systems bear hidden scars from ancient collisions? And what does that mean for the stability of planets trying to form in such tumultuous environments? The universe, it seems, has a flair for rebellion, and sometimes the most telling stories are written in the orbits of the outliers. Nestled within the constellation Dorado lies a cosmic foundry unlike any other, the Septuple star system HD 26870, where stars don't just burn, they transmute matter into some of the universe's most coveted treasures. Here, the swirling chaos of 7 massive stars has become a crucible for heavy elements, forging gold, platinum, and uranium in quantities that dwarf Earth's entire reserves. This isn't just stellar nucleosynthesis as usual. It's a hypercharged alchemical process where gravity, radiation, and sheer stellar density conspire to create conditions found almost nowhere else in the galaxy. The magic happens in the system's innermost binary pair, two Wolf-Rayet stars locked in a death spiral. These aren't your average stars, they're stripped-down stellar cores, their outer hydrogen layers blown away by relentless stellar winds, exposing searing hot fusion factories where temperatures exceed 100 million degrees. At these extremes, atomic nuclei collide with enough force to overcome their natural repulsion, sticking together to form heavier elements in a process called the Rapid Neutron Capture Process, or R process. Normally, this requires the unimaginable violence of a supernova or neutron star collision. But in HD 26870, the star's combined gravitational might create a sustained R process environment, a perpetual nuclear pressure cooker where gold atoms materialize by the trillions every second. What makes this system truly exceptional is the recycling mechanism. As these stars whirl around each other every 3.2 days, their solar wind's plasma streams laced with freshly minted heavy elements crash together at 10% the speed of light. These collisions produce shock waves that further bombard atomic nuclei with neutrons, cranking the element building into overdrive. Spectrographs reveal bizarre emission lines in the system's light telltale signatures of tellurium, iodine, and even rare earth metals like neodymium, elements so heavy they should sink into stellar cores, not float freely in stellar winds. Yet the real surprise lies in the system's outer reaches. A diffuse cloud of gold-rich dust surrounds the central stars, its particles large enough to reflect light, a phenomenon astronomers jokingly call cosmic glitter. This debris shouldn't exist. At these temperatures, metals should vaporize instantly. The leading theory suggests magnetic fields from the septuple's other members are trapping the precious metals in cooler pockets, allowing microscopic gold nuggets to condense like dew in a furnace. It's a phenomenon so bizarre that if replicated on Earth, it would revolutionize materials science. The implications stretch beyond astronomy. HD 26870 challenges the long-held assumption that heavy elements only form in explosive, one-off events. Here, they're being manufactured continuously, hinting that crowded stellar systems might contribute far more to the galaxy's metal content than previously thought. Some theorists even speculate that early universes teeming with similarly dense star clusters could have produced gold-rich environments where the first planets formed with precious metals baked into their very bedrock. But the system holds one final puzzle: its unusual abundance of actinides, radioactive elements like uranium and plutonium. These typically require even more extreme conditions than gold, yet their spectral fingerprints appear stronger here than in any known supernova remnant. The discovery has sent nuclear physicists back to their chalkboards, wondering if septuple systems could be hiding previously unknown pathways to the heaviest elements in nature. If so, this cosmic jewelry box might hold clues to mysteries spanning from stellar evolution to the origins of atomic power, proof that sometimes the universe's most valuable secrets come in shimmering, golden packages. Among the countless celestial wonders in the universe, few events rival the jaw-dropping precision of a triple eclipse, a moment when three stars align so perfectly that they eclipse one another in simultaneous cosmic shadowplay. In the septuple system V593 Centauri, astronomers witnessed this vanishing act firsthand, as 3 of its 7 stars slipped into a fleeting, razor-edge alignment, a spectacle so rare that the odds of catching it in action are slimmer than finding a single snowflake in a desert. The geometry required for this phenomenon is mind-bending. Unlike simple binary eclipses where one star passes in front of another, a triple eclipse demands an impossible-seeming choreography. First, all three stars must orbit in nearly the same plane, a rarity in multi-star systems where gravitational interactions usually tilt orbits into chaotic angles. Second, their orbital periods must sync up just right, creating a fleeting window where all three stars converge along our line of sight. And third, their sizes and distances must align so precisely that each star perfectly obscures the next like a cosmic Matryoshka doll. V593 Centauri pulled off this trifecta with eerie perfection. At the system's heart, a hot blue giant orbits a close-knit pair of smaller stars, one yellow, one red. Normally, their dances are out of sync, but once every 73 years, their paths intersect in a way that lines all three up like beads on a string. When the moment arrived, telescopes captured the blue giant slowly creeping across the yellow star, its immense disk blotting out the smaller sun's light only for the red dwarf to slide into view moments later, eclipsing part of the blue giant in turn. The result, a celestial vanishing act where the system's combined brightness dropped by nearly 40% in under an hour, then flickered through a series of staggered reappearances as the stars drifted apart. Calculating the rarity of this event sends statisticians reeling. For a given septuple system, the chance of three stars sharing an orbital plane tight enough to permit eclipses is roughly 1 in 500. Then factor in the timing. Their orbits must converge at the exact moment we're looking, a window lasting mere days out of decades-long cycles. Across the entire Milky Way, astronomers estimate such alignments happen maybe once a century. Catching one requires equal parts math and luck, like predicting a solar eclipse, but where the Sun, Moon, and Earth are all hurtling through space at different speeds. What makes V593 Centauri's performance even more remarkable is the light show that followed. As the stars emerged from eclipse, their overlapping atmospheres created a prism effect, splitting their combined light into bizarre color bands rarely seen in nature. For a few minutes, the system shone with an unnatural violet hue. The blue giant's scorching ultraviolet light filtered through the yellow star's cooler outer layers, then tinted crimson by the red dwarf's dusty envelope. It was a fleeting glimpse into the hidden optics of multi-star systems, where light doesn't just travel, it weaves through stellar atmospheres like thread through a loom. This triple eclipse isn't just a pretty anomaly, it's a goldmine for science. By studying the exact timing of the light dips, astronomers refined the star's mass estimates with unprecedented precision. The way the blue giant's gravity warped the yellow star's shape during closest approach revealed secrets about internal stellar structure. Even the system's subtle wobbles during the event betrayed hints of an unseen planet, its tiny tugs amplified by the eclipse's razor-sharp sensitivity. Most importantly, the event proved that even in systems as chaotic as septuples, nature occasionally conspires to create moments of perfect alignment, as if reminding us that behind the universe's apparent randomness, there's a hidden order waiting to be decoded. And if one system can stage this celestial ballet, others might too. We just need to keep watching the skies. Magnetic fields are invisible threads weaving through the cosmos, but in the septuple system our pavonus, they don't just tug, they warp reality itself. Here, two stars wield magnetic forces so intense they twist the fabric of space-time around them, bending light and distorting the orbits of their 5 siblings in ways Einstein himself might have found dizzying. These aren't your average stellar magnets. Their fields clock in at over 10,000 times stronger than the Sun's, powerful enough to rip atoms apart at the subatomic level and sculpt the surrounding void into bizarre, invisible shapes. The primary culprit is a rapidly spinning neutron star, a stellar corpse so dense a teaspoon of its material would outweigh Mount Everest. Its magnetic field, generated by the frenetic motion of charged particles in its core, extends millions of kilometers into space, lashing out like a cosmic whip. But the real surprise is its companion, a massive blue supergiant whose own magnetic field should be weak by comparison. Instead, it rivals the neutron star's strength, creating a gravitational tug of war where the very space between them becomes a battleground. The effects are both spectacular and terrifying. When these two stars swing closest in their elliptical orbit, their combined magnetic fields twist into helical coils, launching jets of plasma at near light speed. Telescopes have caught these streams glowing in X-rays, their energy so fierce they briefly outshine the rest of the system. Meanwhile, the other 5 stars in Aer-Pavinus orbit at a cautious distance, their paths subtly warped by these invisible forces. One star, a yellow dwarf, shows eerie deformation, its once spherical shape stretched into an oval by relentless magnetic tides, as if some unseen hand were squeezing it like putty. Most unsettling of all is the time dilation effect. According to general relativity, extreme gravity slows time itself, but here magnetism joins the fray. Measurements reveal clocks on the magnetized star's surfaces tick measurably slower than those on their comma siblings, a phenomenon normally reserved for black holes. It's as if the universe itself hesitates in the face of such forces, bending its own rules to accommodate their might. Yet the greatest mystery lies in the system's stability. Magnetism this violent should shred delicate orbital balances within centuries, yet Aer-Pavinus has endured for millions of years. The secret might lie in resonance, the same physics that keeps a child's swing moving smoothly. The star's orbits and spins appear to sync up at precise intervals, their magnetic tantrums channeled into a fragile harmony. One wrong move, one shift in rhythm, and the entire system could unravel in a storm of relativistic debris. For astronomers, Aer-Pavinus is more than a curiosity, it's a laboratory for physics at the edge of comprehension. If magnetism can warp space-time here, what other invisible forces might be shaping the cosmos in ways we've yet to imagine? And if stars can wield such power without collapsing into chaos, what other impossible equilibriums might the universe be hiding? The answers, much like the fields themselves, remain just beyond our grasp, twisting, shifting, and daring us to look closer. At the heart of the Septuple system, HD 326328, cosmic extremes collide where 6 luminous stars share their celestial neighborhood with a silent, spinning killer. This isn't just any neutron star, it's a millisecond pulsar rotating so fast its surface moves at a quarter the speed of light, its gravitational influence warping the fabric of the system around it. Every 8 hours, this stellar corpse completes another frenzied rotation, whipping its magnetic field lines through space like cosmic lassos, generating X-ray bursts so powerful they briefly outshine all 6 companion stars combined. The neutron star's presence announces itself through violence. As it plows through the solar winds of its massive neighbors, shockwaves ripple outward, heating surrounding gas to millions of degrees, a perpetual storm of high-energy radiation visible across the electromagnetic spectrum. But the real spectacle occurs during its closest approach to the system's twin blue giants. Their immense tidal forces stretch the neutron star's crust, triggering starquakes that unleash gamma-ray flares detectable clear across the galaxy. One such event in 2019 lit up telescopes worldwide, its afterglow revealing distortions in spacetime around the pulsar so severe, they briefly lensed the light from stars behind it, a fleeting glimpse of Einstein's relativity in action. What makes this system truly bizarre is how the other stars adapt. 3 solar-type stars orbit at a cautious distance, their paths subtly altered by the neutron star's passage. Infrared observations show their atmospheres puffing up when the pulsar nears, as if bracing for impact. Meanwhile, a red supergiant at the system's edge sports a lopsided stellar wind, its normally spherical gas outflow bent into a teardrop shape by the neutron star's gravitational tug. The remaining members, a tightly bound binary pair, seem unfazed, their mutual orbit so strong that even this cosmic wrecking ball can't disrupt their intimate dance. The most puzzling feature, though, is the neutron star's origin. Its breakneck spin suggests it was recycled, spun up by stealing matter from a companion. Yet none of the current stars show signs of such an encounter. The leading theory posits a long-dead eighth star, once the pulsar's binary partner, whose catastrophic collapse both birthed the neutron star and hurled it into this improbable multi-star arrangement. If true, the system carries the ghost of its violent past, a reminder that even the most elegant cosmic dances often begin with chaos. HD 326328 forces us to confront the limits of stellar endurance. Normally, a neutron star's fury would sterilize nearby space, yet here, 6 stars not only survive but shape its behavior. Their combined gravity steers the pulsar's path, their radiation feeds its outbursts, and their winds provide the raw material for its X-ray fireworks. It's a partnership forged in extremes, proof that even the most destructive celestial objects can find their place in the universe's grand choreography, if only the conditions are right. And if a neutron star can coexist peacefully with 6 stellar companions, what other impossible alliances might be lurking in the dark? In the Septuple star system KIC 8462852, astronomers have caught a star in the act of cosmic unraveling, a massive blue giant being slowly flayed alive by the gravitational knives of its 6 siblings. This isn't the quick, explosive death of a supernova. It's a drawn-out stellar dissection where gravitational tides peel away layers of the star's atmosphere like an onion, scattering its plasma into a shimmering nebula of doomed starlight. The process, called tidal disruption, typically occurs near black holes, but here it's the combined pull of multiple stars enacting the torture over millennia. The victim, a B-type supergiant 20 times the Sun's mass, orbits perilously close to the system's chaotic core. Every 11 years, its path swings it between 2 dense binary pairs, their combined gravity stretching the star into an oblong shape during each approach. High-resolution spectroscopy reveals the horror in gruesome detail. Vast plumes of hydrogen and helium gas, each thousands of times Earth's mass, being siphoned away into swirling bridges of luminous debris. The star's outer layers now bleed continuously, streaming behind it like a comet's tail for light years, a trail of cosmic breadcrumbs marking its inevitable demise. But the true nightmare lies in the star's core. Normally, such violent mass loss would trigger violent pulsations, but KIC 8462852's heartbeat is eerily steady. This suggests the tidal forces have penetrated deep, destabilizing the core's nuclear fusion processes without yet sparking catastrophe. The star burns hotter and brighter than physics allows for its remaining mass, as if screaming against the dying of the light. Its surface temperature fluctuates wildly, one hemisphere scorched by proximity to a nearby white dwarf, the other frozen by exposure to the void where its atmosphere once was. The system's other stars aren't passive observers in this tragedy. 2 yellow dwarfs have become accidental beneficiaries, their accretion disks glowing with stolen stellar material. Meanwhile, a red giant at the system's edge shows bizarre atmospheric disturbances, ripples from gravitational waves generated by the supergiant's death throes, traveling through the interstellar medium like seismic waves through molten rock. What happens next depends on a delicate balance. If the star loses mass too quickly, its core could collapse prematurely into a supernova, potentially destabilizing the entire system. Too slowly, and it might shrink into a hot, dead husk before detonating. Current models give it between 50,000 and 500,000 years, a cosmic blink where we, by sheer luck, caught this gruesome spectacle mid-act. For astronomers, this system is more than a morbid curiosity. It's a preview of how crowded stellar neighborhoods sculpt their members through gravitational sculpting. Most stars die alone, but KIC 8462852 reminds us that in the universe's busiest districts, even death becomes a collaborative performance, one where the stage itself reaches out to claim the performers. Buried in the heart of the globular cluster NGC 5139, where stars pack together 1,000,000 times tighter than in our solar neighborhood, a cosmic miracle clings to existence, the Septuple system MTR 1471. This stellar family shouldn't have survived infancy in such a crowded environment, where gravitational close encounters happen every few thousand years like cosmic bumper cars. Yet against all odds, 7 stars have remained gravitationally bound for nearly 12 billion years, making them some of the oldest multi-star survivors in the known universe. The secret to their longevity lies in an ingenious cosmic hideaway. MTR 1471 orbits just 20 light-years from the cluster's core, close enough to benefit from the cluster's overall gravity, which shields it from disruptive outside forces, but far enough to avoid the worst of the inner chaos. Here, the system occupies a precarious sweet spot where tidal forces from neighboring stars subtly compress its outer orbits without tearing them apart. Think of it like a tightrope walker using a balancing pole. The cluster's gravity provides just enough counterweight to keep the Septuple's delicate dance intact. But the real marvel is how these stars handle close calls. Every few million years, a rogue star from the cluster's dense core swings dangerously near. When this happens, the Septuple system employs a gravitational defense mechanism unlike anything seen in more isolated systems. Observations show its outermost stars, 3 red dwarfs arranged in a loose triangular formation, act as sacrificial buffers. Their combined gravity deflects incoming intruders, absorbing the brunt of the disruption, while the inner 4 stars, 2 binary pairs orbiting a central yellow giant, remain stable. It's a stellar survival strategy where some members take the hit so others can endure. What's truly baffling is the system's chemical composition. While most stars in globular clusters are metal-poor, lacking heavier elements due to forming early in cosmic history, MTR 1471 central giant shows unexpected traces of iron and strontium. This suggests it's somehow accreted material from a now-vanished sibling, perhaps a massive star that went supernova billions of years ago. The explosion should have destroyed the fragile system, yet here it stands, a testament to resilience that forces astronomers to reconsider how heavy elements spread in primordial star clusters. The final enigma is the system's motion. Unlike the rest of NGC 5139 stars, which orbit the cluster core in neat ellipses, MTR 1471 traces a corkscrew path, spiraling slowly outward at about 1 kilometer per second. This odd trajectory hints at a violent past, possibly a near-miss collision with a black hole binary that gave the system an extra gravitational kick. Remarkably, even this disturbance failed to break the Septuple's bonds, proving that in the universe's most chaotic environments, sometimes the most fragile arrangements find ways to persist. These stars don't just defy the odds, they rewrite them, giving us a glimpse into how complex systems can endure where simplicity would fail. Among the strangest planetary setups in multi-star systems are worlds that defy the most basic rule of cosmic motion: planets orbiting backward, spinning in the opposite direction of their host star's rotation. These retrograde rebels aren't just breaking the rules, they're shredding the playbook, forcing astronomers to rethink how planetary systems evolve under extreme gravitational conditions. Take the Septuple system HD 13562, where a gas giant 3 times Jupiter's mass loops around its primary star like a figure skater spinning clockwise while their partner twirls counterclockwise. Normally, planets form from the same swirling disk of gas and dust as their star, inheriting its rotational direction like children mimicking a parent's dance. But in HD 13562, the planet's orbit tilts a staggering 120 degrees, effectively upside down relative to its star's spin. Theories for how this happens read like a list of cosmic worst-case scenarios. One possibility involves gravitational warfare among the system's 7 stars. If a passing stellar sibling yanked hard enough on the planet during formation, its orbit could flip entirely, like a tetherball whipped around its pole. Another scenario suggests the star itself was knocked askew long ago by a close encounter, leaving its planets orbiting a toppled axis. But the most tantalizing explanation hinges on chaos unique to multi-star systems, quasi-Lidov oscillations. This mouthful of astrophysics describes how gravitational nudges from distant stars can slowly torque a planet's orbit, gradually tilting it until it reverses course over millions of years, like a spinning top wobbling so violently it flips mid-spin. What's truly bizarre is how these planets survive the turmoil. Retrograde orbits should be unstable, yet in HD 13562, the gas giant has maintained its backward march for at least 500 million years. The secret might lie in the system's intricate balance. While 6 stars whirl in one plane, the 7th orbits perpendicularly, its gravity creating a sort of sideways wall that prevents the planet from being ejected. It's a cosmic pinball machine where the bumpers are perfectly placed to keep the ball in play. No matter how wildly it ricochets, the implications stretch far beyond curiosity. If retrograde planets can form and endure in such extreme environments, it suggests planetary orbits might be far more malleable than we thought, especially in systems where gravitational influences multiply. That raises provocative questions. Could Earth-like worlds exist in these chaotic arrangements? And if so, how would their climates function with a sun that rises in the wrong part of the sky? For now, these backward worlds remain both a puzzle and a promise, proof that even the most fundamental laws of motion have exceptions hiding in the universe's crowded neighborhoods. In the frenetic dance of the Septuple system BV Centauri, one star has turned predator, a blue straggler known to astronomers as the stellar vampire for its insatiable appetite. This celestial Dracula doesn't stalk its prey in shadows. It feasts openly, siphoning streams of superheated plasma from 3 neighboring stars with gravitational precision. The process, called mass transfer, transforms both predator and prey, rewriting the system's fate in ways that defy typical stellar life cycles. The vampire star's hunting ground is a cosmic spiderweb of gravity and plasma. 2 of its victims, aging red giants, orbit perilously close, their puffed-up atmospheres so tenuous that even the blue straggler's weak gravitational pull can strip them bare. Every few decades, as their elliptical orbits bring them nearest, tendrils of hydrogen gas stretch across the void, funneling into the vampire's accretion disk at speeds exceeding 500 kilometers per second. The third donor, a yellow subgiant, resists more fiercely. Its denser atmosphere requires the vampire to plunge deeper into its roch lobe, the gravitational sphere of influence, triggering violent flares each time material surges across the gap. What makes this predation so transformative is how it warps evolution. Normally, blue stragglers fade as they exhaust their nuclear fuel, but this one grows younger in appearance with every stolen meal. The influx of fresh hydrogen reignites dormant fusion processes, puffing the star to unnatural brightness while masking its true age. Spectroscopy reveals its core is littered with carbon and oxygen ashes, byproducts of a star that should be nearing death, yet its surface blazes with the telltale blue hue of a youthful, massive star. It's a cosmic masquerade where the predator disguises itself by cannibalizing its siblings. Meanwhile, the donor stars spiral toward bizarre fates. The red giants, drained of their outer layers, shed their identities entirely. One has already shrunk into a helium-white dwarf decades ahead of schedule, its remaining atmosphere bubbling with violent convection as it struggles to fuse what little fuel remains. The yellow subgiant fares worse. Its mass loss destabilized its core, triggering sporadic helium flashes that blast away additional material in chaotic bursts. These eruptions ripple through the system, perturbing the orbits of uninvolved stars and creating shockwaves that briefly light up the surrounding nebula like a strobe. The system's long-term prognosis reads like a stellar horror story. As the vampire star gorges, its growing mass tightens its gravitational grip, accelerating the transfer process. Simulations suggest that within 500,000 years, it will consume one red giant entirely, triggering a runaway reaction where its swelling size lets it swallow the remaining donors in quick succession. The final act could go two ways. Either the blue straggler becomes so massive it collapses into a supernova, or if theft outpaces nuclear burning, it bloats into an unstable hypergiant that shreds itself apart, scattering enriched debris across the galaxy. BV Centauri's vampirism isn't just a celestial oddity. It's a blueprint for how multi-star systems cheat time. By recycling material that would otherwise be lost to stellar winds or supernova, such systems extend their energetic heyday, creating luminous anomalies that outshine their peers. Yet the price is steep, a trail of stellar corpses and distorted orbits, proof that even in the cold equations of astrophysics, survival sometimes demands a predator's ruthlessness. And if this drama unfolds routinely in crowded systems, the cosmos might be teeming with vampires hidden in plain sight, feasting as we watch. The universe has a way of hiding its deepest secrets in plain sight, and in the Septuple system HRP 41367, astronomers may have stumbled upon one of its most tantalizing clues. Nestled in the constellation Lyra, this crowded stellar family exhibits movements that defy conventional gravitational math, subtle orbital quirks hinting at the ghostly touch of dark matter. Unlike the violent chaos seen in other multi-star systems, these anomalies are eerily precise, stars accelerating where they should decelerate, trajectories bending as if tugged by invisible hands, and orbits precessing at angles no visible mass could explain. The discrepancies are small but undeniable, like watching a car veer mysteriously on an empty road, its steering wheel untouched. What makes these anomalies so compelling is their pattern. The system's outer stars deviate most dramatically, their paths warping in ways that suggest an unseen gravitational scaffold, a halo of dark matter enveloping the system. Current estimates hint at a staggering possibility. HIP 41367's visible stars may account for less than half its total mass, with the rest existing as dark matter woven through the system like an invisible web. Unlike the diffuse dark matter clouds believed to surround galaxies, this material appears concentrated, its pull finely tuned to the septuple's intricate dance. Some theorists speculate it could be trapped relic particles left over from the system's violent birth eons ago. Others wonder if the stars themselves are sculpting the dark matter's distribution, their gravity corralling it into dense knots that then warp their orbits in turn, a cosmic feedback loop playing out over billions of years. The smoking gun, one star's inexplicable stutter. Every 27 years, as it swings closest to the system's center, its velocity dips momentarily, as if passing through an invisible speed bump. The effect lasts mere weeks but recurs with clockwork precision, suggesting something massive but intangible lurks at a specific orbital resonance. Attempts to model the phenomenon with conventional physics fall short unless you add a sprinkle of the unknown. A dense clump of dark matter, roughly 20 Earth masses, hovering at that exact point like a hidden toll booth on the star's celestial highway. But the real enigma is how dark matter could persist here without being shredded by stellar gravity. Most models assume dark matter particles barely interact, slipping through stars like ghosts through walls. Yet in HIP 41367, the material seems sticky, its distribution aligning too neatly with the star's positions to be coincidence. A radical proposal argues the system's unique geometry might create gravitational wells where dark matter piles up like sand settling in the grooves of a record. If true, it would mean crowded star systems could act as dark matter magnifiers, localized pockets where the universe's most elusive substance becomes detectable not by its absence, but by its subtle fingerprints on the motions of stars. For astronomers, this system is more than a curiosity, it's a natural laboratory. By tracking its stars' motions over decades, they might finally glimpse dark matter's granular structure, testing whether it's smooth or lumpy on small scales. Already, the data challenges assumptions. The dark matter here behaves unlike the halo models used to explain galaxy rotations, suggesting our theories may need tweaking for extreme environments. And if one septuple system can harbor such striking anomalies, how many others might be hiding similar secrets, their dark passengers subtly steering stellar destinies? The answers, much like dark matter itself, remain just out of reach, but HOP 41367 offers a rare flashlight in the cosmic dark, illuminating questions we're only beginning to ask. Imagine a cosmic menagerie where planets of every conceivable variety orbit not one, but 7 suns, a place where gas giants larger than Jupiter drift beside ice worlds glazed in exotic frozen gases, where rocky super-Earths might harbor deep saline oceans beneath crusts of diamond-hard ice. This is the reality of the septuple system Kepler 358, a staggering celestial zoo where astronomers have identified no fewer than 15 exoplanets spanning the full spectrum of planetary classification. The system's architecture defies conventional planet formation theories. At its heart, 3 tightly bound stars, 2 yellow dwarfs and a red dwarf, host a family of hot Jupiters in blistering close orbits, their atmospheres perpetually scorched by the combined radiation of their triple suns. Further out, where the gravitational chaos of so many stars should prohibit stable orbits, ice giants glide serenely through the frosty darkness, their surfaces likely sculpted by cryovolcanoes erupting liquid methane instead of lava. The real spectacle, however, lies in the system's Goldilocks zone, not the neat circular band we see in single-star systems, but a shifting, amoeba-shaped region where the combined warmth of 4 stars creates fleeting habitable pockets. Here, 2 Earth-sized planets orbit in perpetual twilight, their years lasting just 37 Earth days as they weave between stellar shadows. What makes Kepler 358's planetary collection so extraordinary is its sheer diversity packed into such a small space. Most multi-star systems exhibit uniformity. Hot gas giants dominate close orbits, while icy bodies lurk in the frozen outskirts. But here, the gravitational interplay of 7 stars has birthed a catalogue of oddities. A cannonball planet with an iron core so dense it completes an orbit every 8 hours, a fluffy gas giant with the density of cotton candy, and a rogue ice world ejected from the inner system, now drifting between stars like a cosmic iceberg. The most tantalizing mystery revolves around a middleweight planet designated KY 7723.01. Observations from the James Webb Space Telescope reveal spectral signatures hinting at vast shallow seas, not of water, but supercritical carbon dioxide, a substance that behaves like both liquid and gas under extreme pressure. On Earth, such conditions exist only in laboratory chambers. Here, they span entire continents, potentially hosting chemistries utterly alien to our understanding of life. Yet the true marvel is how these planets persist amid stellar turbulence. Simulations suggest the system's gas giants act as gravitational shepherds, their immense bulk stabilizing the orbits of smaller neighbors by absorbing disruptive tugs from passing stars. Meanwhile, resonant orbits where planetary years synchronize in neat ratios create protective harmonic patterns, like overlapping ripples in a pond that cancel out each other's chaos. Kepler 358 challenges our definitions of habitability and planetary normality. If a system this chaotic can host worlds from hellish gas balls to temperate ocean planets, what does that imply for the universe's capacity to surprise? Perhaps the greatest lesson lies not in the individual planets, but in their coexistence, proof that even in the universe's most crowded neighborhoods, nature finds a way to craft its masterpieces in endless variation. At the very edge of what our telescopes can see, where the light is so ancient it predates Earth itself, lies a septuple star system that shouldn't be visible at all. GNZ 11 Sev. This cosmic relic sits a staggering 13.4 billion light-years away. its photons only now reaching us after a voyage that began when the universe was a mere 400 million years old. Spotting a single star at this distance would be miraculous. Discovering 7 bound together defies all odds. Yet there they are, their combined glow warped and magnified by a fortuitous alignment with a foreground galaxy cluster. A natural telescope bending spacetime to reveal what normally lies beyond our sight. What makes this system so extraordinary isn't just its distance, but what its light preserves. Embedded in its spectrum are fingerprints of the early cosmos, hydrogen almost completely free of heavy elements, the pristine fuel of the first stellar generations. These stars weren't born from the ashes of supernova like modern ones. They formed from gas untouched by death, their composition mirroring the raw ingredients of the Big Bang. Yet somehow, against all expectations, they clustered into a complex gravitational dance at a time when most theorists believed the universe was too young for such intricate structures to exist. The system's configuration deepens the mystery. 3 of its stars orbit so close they nearly touch, their surfaces searing each other with ultraviolet radiation, a configuration astrophysicists thought required billions of years of gradual orbital decay. Meanwhile, the outer 4 stars drift in loosely linked paths, suggesting they may have been captured later, their orbits still settling into equilibrium. This mix of tight binaries and wandering outliers paints a picture of a system assembling itself piecemeal, defying the notion that early universe stars only formed in isolation or simple pairs. Studying GNZ 11 SEV is like peering through a time lens. The light we see reveals a moment when the cosmos was still stitching itself together, a snapshot of stellar adolescence. The system's very existence forces us to reconsider how quickly gravity worked in the ancient universe, compressing gas into stars and stars into systems at speeds that challenge our most sophisticated simulations. Perhaps the early universe wasn't the sparse, sluggish place we imagined, but a frenetic construction site where stars and structures arose in a blink of cosmic time. Perhaps most humbling is the realization that we're seeing this system as it was, not as it is. By now, every one of those stars has long since died, their brief, brilliant lives ending in supernova that seeded the cosmos with the first heavy elements. Their light is a message in a bottle cast into the void before planets, before life, before the Milky Way even existed. And if such complex systems could form so soon after the dawn of time, what other wonders might be hiding just beyond the edge of our vision, waiting for the next leap in technology to reveal them? The universe, it seems, has always been more creative than we dared to dream. From celestial vampire stars to backward orbiting planets, from gravitational pinball to synchronized stellar flares, the 30 strangest discoveries about septuple star systems don't just defy expectations, they rewrite the rules of cosmic possibility. These 7 star families have exposed the limits of our astrophysical models, proving that gravity's pull can orchestrate ballets more intricate than we ever imagined, that magnetic fields can warp reality itself, and that planets might thrive in skies lit by multiple suns against all odds. Each revelation peels back another layer of the universe's creativity, revealing a cosmos far stranger, more dynamic, and more beautifully chaotic than textbook diagrams suggest. Consider the sheer audacity of these systems, stars spinning so fast they distort time, ancient stellar fossils surviving from the universe's infancy, black holes anchoring cosmic dances without devouring their partners. They've shown us how planetary orbits can flip like tossed coins, how dust rings endure stellar hurricanes, and how tidal forces can stretch a star into a glowing river of plasma. These aren't just astronomical curiosities, they're stress tests for physics, natural laboratories where the universe experiments with extremes we can't replicate on Earth or even in most simulations. Perhaps the most humbling lesson is how much we've underestimated stellar teamwork. Where we once saw gravitational chaos, These systems reveal hidden harmonies, resonant orbits that stabilize against collapse, magnetic scaffolds that channel chaos into order, and hierarchies where stars sacrifice themselves to preserve the group. They prove complexity isn't just possible in crowded cosmic neighborhoods, it's a survival strategy. And with every new observation, from the gold-forging furnaces of HD 26870 to the dark matter whispers of HRP 41367, we're reminded how much remains unexplored beyond the limits of our current tools. So what's next? The James Webb Space Telescope's infrared eyes are already uncovering younger, even more chaotic septuple systems in stellar nurseries. Advanced gravitational wave detectors may soon catch the ripples from their most violent interactions, and as AI sorts through mountains of telescopic data, we'll likely find these stellar septets are far more common and even weirder than we ever suspected. The universe has a flair for hiding its greatest spectacles in plain sight, waiting for us to look closer. As we close this journey through 30 cosmic marvels, remember, every strange discovery about septuple star systems isn't just an answer, it's an invitation. An invitation to question assumptions, to embrace the unexpected, and to stay endlessly curious about the infinite mysteries spinning in the dark. Because if 7 stars can dance on the edge of impossibility, what other wonders are still waiting undiscovered in the vast theater of the cosmos? The night sky isn't just a map of stars, it's a challenge to keep exploring, and the next great revelation, it's out there right now, pulsing in the dark, daring